Hi, good morning, everyone. I just wanted to post a quick lecture today with a review for exam 3. So just as a quick reminder, this exam will be on chapters 7 through 9. And this one will be available from Friday through Sunday again, just like the last exam we had. And it will also have a 50-minute time limit. In structure and form, it's going to be nearly identical to the previous exam with the multiple choice section, the short answer sections, and yeah, hopefully you'll know what to expect there. So I don't want to spend a lot of time talking about the exam itself because you guys are pretty familiar with that now. I will also have one extra credit problem again. So please make sure to save time to do that one. That can only help you out. It will likely be drawing again with an upload. Again, if you can't get it to upload, you can always email that to me. Well, so let's go through the individual chapters now, and I'm just going to hit some of the highlights here and mention a few things. So the first chapter is chapter 7. Chapter 7.1 basically is looking at where can we find the ingredients for life, primarily in the solar system. So those ingredients are building blocks, primarily organic molecules. Remember, those are carbon containing. Also energy. And here in this chapter, we focus mostly on sunlight because that is a huge energy source for life. And also liquid water. We need that solvent for life. So basically going over these three things and where we might be able to find them in the solar system. 7.2, we started taking a tour of the inner solar system with respect to life. The first places we looked at were the moon and Mercury. Basically, there's very little chance of finding life there. There's very little water. And what there is locked up in frozen water, scattered around in some craters, mostly at the poles. And there's no atmosphere that we know of. So, yeah, not a very good place to look for life. The next place we focused on was Venus. And while it does have a thick atmosphere, it's way too hot there and way too dry. Now, there may be some liquid water in the clouds. The conditions may be right high up in the atmosphere to have small water droplets. There's a possibility that there could be some bacteria or other microorganisms living up in the upper atmosphere. The last place we looked in the inner solar system was Mars, and there's lots of possibilities here. Mars is a great place to look for life. Such a good place that we'll actually revisit it in a later chapter. So we didn't even look at it in too great a detail here. We just say it's a great spot and moved on. 7.3. We continued our tour of the outer solar system, and that was looking at the Jovian planets. Now, they have no surface, so that's a bit of a problem. It's hard to have lakes of liquid water, something like that, if there's no surface. Again, there may be water up in the atmosphere, like at Venus, but there are strong vertical winds, which make it unlikely to have water there. So we'll put unlikely to have life there. So the Jovian planets themselves are not really good places to look for life. They're either too cold, too hot, too high a pressure, no surface, just not a lot of good things there. Now the moons, and other small bodies, those being like Kuiper belt objects. Now these could contain liquid water. This makes them a great place to look for life, such a great place. Again, we revisit those in detail in a later chapter. Suffices to say for now that they're great places to look for life. Now 7.4, we looked at some spacecraft missions. And the things we looked at there was the different types of missions. What were their advantages and disadvantages? These were things like flybys, orbiters, landers and probes, sample return missions. What were the advantages of those different things? You should know those. Another thing we talked about briefly was humans versus robots. What's the advantage of sending robots into space? What's the advantage of sending humans into space? So that was a sort of a big picture look at Chapter 7. Basically a quick tour of the solar system, looking at where we might find life and what are the best places to look, and then what types of missions do we use to look for those. All right, moving on to Chapter 8. Now, Chapter 8 is all about Mars. So I said we'd revisit this in a later chapter. This is where we do that. The first part, 8.1, was really looking at the history of Mars and primarily in popular culture. Remember that was with Schiaparelli and the Canali, and basically what did people think historically was their life on Mars. And then we talked about what does Mars look like today. And we focused on the geology, remember Olympus Mons, the atmosphere. Let me see, what do I have written down here? Geology, atmosphere, and evidence for water. So we talked about some different geologic features, the two different regions, the highlands versus the lowlands, the different ages of those. We talked about, like I said earlier, Olympus Mons and Valles Marineris, and some of the evidence that there was water on Mars. We looked at this a little more detail in 8.3. This was looking at the climate history of Mars. And basically, why was Mars wetter in the past? So what did we need? What was needed for those conditions? We talked about having atmospheric pressure, warmer temperatures, things like that. What did we need to have liquid water at the surface? And then we moved on to how or why did Mars lose the water? And that was focused on the loss of the magnetic field, the cooling of the core, solar winds stripping the atmosphere away to the point where there is no longer an atmosphere, so it's not warm enough. There's not enough atmospheric pressure to support liquid water, at least abundant liquid water on the surface. We talked about, is Mars habitable today? And maybe in some localized parts, but not all over. This led into 8.4, asking the question, what is the evidence for life on Mars today? And there were, remember, 3 lines of reasoning. So there were 3, what's the word I'm looking for here? 3 pieces of evidence. That's not really the right word, but remember that was the Viking experiments, methane in the atmosphere, and the Martian meteorites. And then we looked in particular at one Martian meteorite and what was the evidence for that. What was the evidence in the meteorite that there was biotic processes at work there, and how was that evidence refuted? So looking a couple of times here at evidence for life on Mars. So again, big picture of Chapter 8, just Mars in general. So what is it like today? What was it like in the past? What is the evidence for these different things? Is there life today? What evidence do we have to support that theory? What are the ways that that is being refuted? Chapter 9 is kind of a similar to Chapter 8, except for here we were looking at the moons of the outer solar system. So, moons of outer solar system. And basically first looked at their general characteristics. What do their orbits look like? How do we think they formed? We talked about tidal heating quite a bit. That's the energy source that's resurfacing them. That's one of the main characteristics of these things. We see lots of resurfacing going on. And so what are those tidal processes at work? Those were things like resonances, the eccentricity of the orbit. We talked about synchronous rotation. So all of those things. 9.2 was a focus on the Galilean moons. We went into detail on each of those. So just as a reminder, that's Io, Europa, Ganymede, and Callisto. And I can always remember those by saying, I eat green carrots. And so that's a nice little mnemonic to remember those 3 moons. And we found that of all of those, Europa was the most likely to have life. Io, the innermost moon, was way too hot, too much tidal heating, there's no water there. Ganymede may have water, but it's buried deeper, and it may not even be differentiated. And then we get out to, Callisto's the one that may not be differentiated. But regardless, Ganymede and Callisto have less strong evidence than Europa of a global ocean. So Europa probably has a global ocean. We see lots of resurfacing on the surface. We see cracks. We see tectonics. We see lots of stuff going on there. So Europa is probably a great place to look for life, especially below the ice layers. 9.3, we looked at Saturn's moons. Remember, these moons up here are all around Jupiter. For Saturn's moons, we focused on Titan, the largest of the moons. We looked at its atmosphere. Where does it come from? How does it evolve? We looked at the lakes of methane, which also probably contain ethane. And we talked about subsurface water. So a good overview of Titan and whether or not life can exist there. Probably not enough energy for life at Titan, although it could exist maybe in some other form. We also looked at Enceladus, which is a very strange little moon that really makes us rethink of our idea of where and how life can exist. This has a lot of cryovolcanism. Remember the geysers of ice and salt shooting out, water, ice, and salt shooting out of the South Pole along those tiger stripes. So there's a lot of heat coming out of there, probably an ocean under there, but maybe only in the South Polar region, so maybe zones of habitability there. Very interesting moon. The last section we looked at was 9.4, and that was looking at chemical energy. Now, all of these moons that we've talked about are very, very far from the from the sun, and so they receive very little sunlight. That's primarily the main problem. If we think back to those 3 ingredients for life, there are lots of organic molecules out here. All that orange gunk we see on the surface of Europa is likely large organic molecules. There's plenty of that stuff. We have global oceans, lots of liquid water, but very little sunlight, either at the surface and especially below the ice. So if there is life out on these moons, they will almost certainly be getting their energy from chemical processes. And so the 2 key concepts there are chemical equilibrium. When things are not in equilibrium, then we can get we can get reactions going on, and some of those reactions are very energetic, in particular redox reactions. These are reduction-oxidation reactions named after oxygen. Remember when we talked about evolution on Earth, that the rise of oxygen was important because it can provide lots of energy for complex organisms, and it's primarily through these redox reactions. And the main thing to take away from there is that we have charge transfer from one reactant to the other. And in that process of transferring charges around, either increasing their charge or decreasing their charge, we can get a lot of energy exchanged. And so we see both of these things happening at the deep sea vents here on Earth. And so it's likely that these types of chemical reactions and chemical disequilibria is happening at the bottom of the oceans on Europa, and if there's life there, it could be taking advantage of this. So that's about it for my review. I kind of flew through that. There is a study guide on Canvas as well, a written up one, so please take a look at that. I tried to include everything that we covered since the last exam in there. As always, if you have any questions, please feel free to email me. I would be happy to answer any and all questions you have, either regarding content or format of the exam. All right, I hope you're safe out there. Take care and have a great day.